Okay, so the homework, I got the impression, was a little bit more than the previous three, so I'll take that into account and ease back a little bit. I think a bit of the problem is in this class, I don't really teach you technique. We're not really learning techniques of mathematics or whatever. We're sort of going through this broad sweep of history, doing all kinds of different kind of maths. And we're just selecting little problems along the way. So they're not meant to be long problems, really involved problems, but I think you do have sometimes a little problem of knowing how to get started. So anyway, is someone have just a few quick questions they want to ask, or?
3B on the ones you wrote.
Sorry?
3B on the problem that you it's from the PowerPoint. It's like proof that three sides can form a triangle. You can use points 2 and 3 as assumptions.
Right. So with that one, we've got information, those 2 and 3, we've got those two inequalities, like a rectangle equals a square. From those two things, you should be able to figure out the sizes, the relative sizes of the triangle. So i.e. in particular, which is the longest. So if you look at them and actually draw out the rectangles and the squares and look at the sides that are in the segment, you can see that those two statements actually tell you which segment is the longest. And then once you have that, argue by some kind of contradiction. So assume that it's too big, and then you should get a contradiction from the definition of that segment. Remember, the definition is that those two triangles have to be the same area. So prove if something is too big, then the triangles can't be equal. That should kind of do it. So Kristen isn't here today, which is unfortunate. She was the one who talked about eudoxus. Is Jack here? I don't know. Okay. So if you look at the presentations, you'll see that there is a new mathematician rises head, a mathematician called Eudoxus. And he's probably the greatest Greek mathematician that you never heard of, sort of thing. So book 5 and 6 of Euclid is entirely his work. And he also worked in astronomy. He was kind of like one of the major early figures who came up with this whole idea of how the Greeks did astronomy. You'll see it in Jack's presentation about the whole idea of there being spheres around the Earth and that things go around, and they try to do everything with circles. And so one thing you know about astronomy is that if you assume things are going in circles around the Earth, then that doesn't fit with what we see in the night sky. And so they came up with things like epicycles. So because the circle for them was some sort of perfect thing, so everything had to either be in straight lines or circles. And so if a circle doesn't work, then you have circles going around circles. That's called an epicycle. And you can then make things offset. You've got then lots of degrees of freedom to make things work. But the thing I want to talk about Eudoxus is just kind of emphasize how he resolved the problem of incommensurables. So for us, incommensurable means irrational. And so we've seen, for example, that the square root of 2 is an irrational number. And the question is, did this freak the Greeks out? Maybe it did, maybe it didn't. Maybe they worried about it. But also, for them, it was kind of like an opportunity to develop some theory, it led to the Eudoxian solution, which I'll just mention right now. And this enabled them just to prove things with a lot of rigor. So let's see what a problem was. So we've discovered that the square root of 2 is irrational. Okay, and so let's draw then a rectangle whose side is 1 and the other side is square root 2. What's its area? Square root of 2. But hang on, is it? Is the square root of 2 of area the same as square root of 2 of length? I mean, they didn't have any kind of logical way of with numbers, you've got integers, particularly the positive integers. And that's kind of rock solid, you know. You can use that as your starting point, or in set theory, you can do all kinds of fancy things with cardinality of sets, but you can come up with positive integers really easily. Then, once you have integers, then you can get the rational numbers, because then you do quotients of things. And this kind of makes sense, and you can make that kind of rigorous because you can then use the Euclidean algorithm to do things. So for example, here I've got a rectangle. It's 1 by, I don't know, 11/7. And this one here is 1 by 9/8. Okay. So how do we know that this rectangle is 11/7 or 9/8 bigger than this one? Well, it's pretty easy, because what we do is we look at the common measure of 11/7 and 9/8. I don't know what it is, but let's say it's 1/56. Oops. Let's say the common measure is, where's my pen? 1/56, right? Because that's the lowest common denominator of 11/7. Okay, I can cut up the 11/7 side. I can cut that up into 88 little thin rectangles. I've got 88 of them, each of width 1/56. And over here, I can do 63 little rectangles, all of width 1/56. Okay, and you're going to agree that something of base 1/56 times 1 is going to have the same area as 1/1 times by 1/56 there, right? Because they're the same thing. So this thing then has to be in the ratio of 88 to 63. Okay, so we're not really interested in finding the areas of rectangles. We're really interested in making sure that the logical construction of our numbers is rock solid. Okay, so you can do that for rationals. Well, for what we would think is rationals, what they would say would be for commensurable. All these things, 1, 11/7 and 9/8, they're all commensurable. So we're fine. Okay, but now let's have a look. Where's my eraser? Okay, because they wouldn't think of it as a problem as the area of that being square root 2. You know, they would consider this, compare this to the square, 1 by 1 square, and here you've got the length square root of 2 to the length 1. And they would have thought that the problem is this proportion of square root of 2 to 1 of length the same as the proportion of square root of 2 to 1 of area? So how can we do this? Well, Eudoxus came up with the Eudoxian solution, which I'll now tell you about. And it's really, when you see it, you kind of think, you know, is that, how can that be significant? It just seems so weird. But anyway, so we've got two quantities. That's it. Two proportions. We want to know, are those two proportions equal? Now, if there are integers m and n, right, then if a and b are commensurable, a over b is going to equal m over n. Right, that's what commensurable means, that when we look at the ratio, we're going to get some kind of rational number. And so we just cross multiply, and we get that's true. So if there are integers m and n, then an is going to equal bm. And they're going to be equal if and only if the same thing happens with c to d. So cn equals dm. And then everything is commensurable. And there's really nothing to see there. Okay, now the trouble comes in, well, what happens if they're incommensurable? We can never find integers m and n such that we have equality. But what happens then is that a on b is either going to be less than m and n. So if this is an irrational number, it's either going to be less than the rational number, or it's going to be more than. Okay? So in this case, we'll have an less than bm, and in this case, we'll have an greater than bm. And these are going to be the same proportion if this is going to be true. Cn less than dm, and Cn greater than, so that's an m, dm. Okay, and this is going to be true for all possible integers m and n. So it's a really nice little subtle definition, but basically what they're using, if you look at the beauty of it, you're seeing that you're using the rationals then to define what's basically the real numbers. So not just, you know, anything. And we know this works. Why does this work? What bit of 21st century knowledge do we have that the Greeks didn't have about how the rationals lie within the reals? Anyone done some topology? You might have done this in foundations. How do the rationals sit within the reals? The rationals are countable, the reals are uncountable, but there's a word. Really, really heavy. Dense, yeah. So there's always a rational number as close as you like to any irrational number. Okay, so this is really why this kind of thing works. Okay, so AB is the same proportion as CD if this is true. And now we can go back to our problem over here, right? And so what we just do is, you know, we've got square root of 2 and 1. We just look at all possible rational numbers, and we compare square root 2 to rational numbers. And so what's going to happen is if we have multiples of this and multiples of 1, if this multiple of square root of 2 is greater than the other multiple of 1, then this area is going to be greater than the corresponding multiple of this area is going to be greater than the corresponding multiple of that area. And if we have a different set of m and n, such that our multiple of square root of 2 is less than our multiple of 1, then the corresponding area of this rectangle, multiples of this rectangle, are going to be less than the corresponding multiples of that rectangle. And everything becomes logically kind of consistent then, and Euclid then proceeds to prove all kinds of things based upon this. Okay, so from the fact, for example, there's one proposition of Euclid which says that if you've got triangles of the same height, then their areas are proportional to their bases. Okay, that's obvious for us, right? Because we know what the formula for area of a triangle is half base by height. So if they've got the same height, then we know that, you know, if we double the base, we double the area. Okay? That follows for Euclid, it follows from this proposition that he proves that triangles with the same base and the same height have the same area. Okay, he can actually prove that using his methods. Once you have that, it then follows that multiples, like if your base is an integer multiple of the other base, then the area is an integer multiple of the other base, because you can cut up the triangle so say it's the base is twice, then you can cut the base in two, and you end up with two triangles. Each of these triangles has the same area as the given triangle with the same base and height. Okay, so it follows for integers. It then follows for rational multiples, because all you do is you find use Euclidean algorithm to find the common measure, and then you've just got then integer multiples of that common measure. And once it's true for that, then it's true for all quantities, because then you use the Eudoxian solution, which says, well, when this collection of triangles is bigger than that, that's going to be true when the same thing can be said of the bases, when the multiples of the bases are greater than whatever multiple we have over there, or the other way around. So you can then prove that proposition following using this thing. It's pretty smart. Actually, has anyone seen Dedekind cuts? So it's basically, you can reword it. So when Richard Dedekind in the 19th century came to the defining the reals, he used a method which is actually kind of logically the same as this Eudoxian solution. So I wanted to share that with you. Okay. Any questions about any of that? Okay. So I want to finish up talking about geometry in medieval Islamic times. So this finishes up chapter 3. There's other things in it, but I'm not going to do that. And I want to look at things which are distinctively Islamic. So let's look at Islamic art for a little bit. So as it's well known, there's kind of like this kind of prohibition about kind of using human form in their art. That's not strictly true. It's not actually in the Quran that you can't do that. It's actually what's known as hadith, which is like a saying that comes from Muhammad. But it's definitely true in religious art, which is very important, and particularly back in medieval Islamic times. So you can't sort of do figurative art. So what do you use instead? So there's something called the arabesque, which is a kind of, it's kind of like a vine, so it's like a vegetation kind of thing. It's kind of like a vine that sort of comes like in swirls and that. So you can use inspiration from vegetation. You can use calligraphy. So Arabic and Chinese are probably the two great written language cultures. But in both Chinese and Arabic, calligraphy is considered very important art. It's been treasured for like centuries, like thousands of years, even in the Chinese case. And that's for very important sort of cultural reasons. In Islam, it's because, you know, that's what the Quran is written in. So they don't really think it's proper to, well, if you translate the Quran, it loses its kind of like its specialness. So it's, you study it in Arabic. And so, you know, you do it over this kind of wide region. So the written language becomes very important. Same thing in Chinese. We always tend to think about Chinese as one language, and it's not. Pity Anna isn't here, she could probably tell us about this. I mean, China is basically as big as Europe, and there are actually, Chinese consists of different languages. Shanghaiese, there's Cantonese, there's Mandarin, whatever. And when they speak, they really can't understand each other a lot of the time when they're speaking their own local language or dialect. But the written language is the same across all the different varieties of Chinese. So it's a really important thing which kind of unifies the country. And it's something that's been since, you know, it's been there for thousands of years, this thing. So calligraphy is important. And so in here, this is a page from a Quran. And it's really hard even sometimes to pick out the calligraphy. It's this white writing here. It's kind of very stylized form of writing. It's a type of writing which is called Kufic. Which is an old form of Arabic. And of course, the other thing that they use is geometric designs. And so this is a really, I love this work because it's got the calligraphy, it's got the sort of geometry, and you can kind of see all kinds of, it seems a little bit like vegetation forms here, like flowers or something like that in there. Okay. So geometry was very important to their arts and crafts, and so it was actually an important part of their education, for craftsmen's education, to actually to learn geometry. And so there were kind of like special books for them for their particular kind of geometry, the things that they would have to make. And the other thing interesting about it is, you know, there's a lot of geometry in their art, and we tend to think about geometry and art as kind of being like different things, as kind of geometry is somehow kind of sterile. But if you look at it, so the wonderful thing about Islamic art is that they use geometry in their art, and they really use it in really kind of interesting ways, so that your eye is just naturally drawn into it. And so a really standard thing to do would be like, if you want to decorate something, you know, of course, particularly if it's something religious, you know, you want to make it really special. And so they would like to cover the whole space, and that kind of makes the space special. And so here for example, we see what we would in math, we know this is a tessellation, right? So there's two basic shapes there that you're using to tessellate. But then through the use of color and sort of other forms here, they make the space really interesting, something that you can just sort of look at. And, you know, if you're being religious, you can contemplate, you can meditate, you can pray in this kind of situation. So, for example, this is, you know, inside a mosque. This is the ceiling, and it's really kind of wonderful. The use of color is really, really special. You know, so obviously, it looks like there's some gold put in there, and there's all kinds of so a lot of the way that geometry is put in there is by the use of symmetry, right? And so you can kind of see like little motifs which are just repeated again and again and again forever. And, you know, you can think of this as having some kind of religious meaning. It's like the finite and the infinite, like it's yourself being in God, that kind of thinking that goes into it. I love this. This is just like a hand warmer. But again, you can see really wonderful sort of decoration, making the space covering the sphere like really, really special. And another thing is that they do tessellations, and they not only do tessellations in 2 dimensions, they can do tessellations in 3 dimensions. And this is something called a mukana. And it's kind of space, but it's, you know, it's got cavities in it, so it's kind of like 3-dimensional. And, you know, there's all kinds of special geometry textbooks for craftsmen to learn how to do these kind of special spaces. And they can do it in all kinds of material. Here it is in stone. Here it is in some kind of glass. Pretty cool. Okay, and as well, if you look at Islamic buildings, you know, like if you look at places like the Dome of the Rock, or my favorite is the Alhambra in Granada in Spain. Has anyone been to Spain? It's like my #1 building I'd like to see in the world. It's really fantastically ornamentally decorated. Okay, so there were texts aimed at craftsmen. So there was a Hellenistic mathematician, Pappus, in Alexandria. I think it was like in the 300s or 400s. He wrote a treatise called the Mathematical Collection. And in book 8, which was available in Arabic, he talked about geometrical constructions with a straight edge and a rusty compass. So by a rusty compass, it just means you have a compass and you can't change the radius of the circle that you draw. Okay? And so this was thought to be very appropriate for craftsmen to know, so they could, they could have their tools and like a rusty, because really any compass, you can't just have infinite flexibility of how big you can make your things. To some extent, all compasses are restricted somehow. And so this inspired books like A Book of Spiritual Crafts and Natural Secrets in the Details of Geometrical Figures by Al-Farabi, who worked in Baghdad and Aleppo in the early 900s. And I want us to look at this book here on those parts of geometry needed by craftsmen. A very kind of direct title by Abu al-Wafa, someone that we'll see later on when we get to talk about trigonometry. He's an important guy in history too. And he worked in Baghdad in the mid-900s. Okay. So this is a kind of problem. To construct an endpoint A, to construct an end, so you get given a segment and you're told that we need to construct a perpendicular and we're not allowed to go beyond A. So we can think of this as kind of like maybe doing something and there's no material here, so you can't go past that. Okay? Well, you just get your rusty compass. So let's say AC is the radius of your rusty compass. You just mark off C. And then you take your rusty compass again and you mark off D from like base at A and C. And so we know that that's going to make an equilateral triangle because all these things there are going to be the same length. And then you just take DC and you extend it, and you just extend it as far as CD, which remember is the same as AC, which is the rusty compass. So you just use your rusty compass then to measure off that length. Okay, so with the rusty compass, it's kind of hard to transfer lengths. You've only got sort of one length that you can transfer. Okay, and then when we do that, we see we have a perpendicular. Can anyone give me the simple geometry of why this has to be a rectangle if these two things are the same? So we've got a circle centered at D, and the circle is going to pass through E, A, and C. So why does that mean that EAC has to be a right angle? What can you tell me about EC?
D is the midpoint of it.
Hmm?
D is the midpoint of EC.
Right. And so what do we call that midpoint? So there's a circle that goes through E, A, and C.
So would D be the center of the circle?
It'll be the center of the circle. This would be a diameter. Right? And we all know that triangles on a diameter and the side of the circle make right angles. Okay. I've mentioned this one before, dividing an interval into an equal number of parts. So you're given AB, and let's say you're asked to divide it into 3 equal parts. Well, you put in the perpendiculars opposite each other. You know how to do that from the previous problem. And then you just get your rusty compass and you mark off equal lengths there and equal lengths there. And then you just go top to top, like this. And the segment is cut into equal parts. And it's kind of easy to see why. Why is that? This triangle is going to be congruent to that triangle, right? Because, why is that? Because, they've got the same angles, right? This is the right angle, this is the right angle. This angle is equal to that angle, equal to that angle, equal to that angle. So they have the same angles, they're similar, but then they have one side in common, so they have to be actually congruent. So that tells us that that is equal to that. And then to show that GD is equal to these guys, or we just see that that triangle EGA is similar to EHG. And so we just write out the relationship of how the sides relate to each other. And when the dust clears after you do the algebra, you see that GD is actually equal to AG as well. So that's pretty straightforward. Bisecting a given angle. Now this is different from how Euclid does it. The way that Euclid does it is he constructs an equilateral triangle here. But we don't need to. In fact, an isosceles triangle is good enough. And an isosceles triangle is what you can easily construct with your rusty compass. You mark off B and G with your rusty compass. So that's the radius there. You then go to B and G and do circles centered there. So you find D, and so that is equal to that. So you've got an isosceles triangle, and so then when you join A to D, since that kind of bisects stuff, since we've got an isosceles triangle here, this bisects that, that's going to end up bisecting that angle over there. So that's pretty good. To construct a square in a given circle. Okay, so the point here is that the circle that you're given doesn't necessarily have to be the circle that comes from your compass, your rusty compass. So it's an arbitrary circle. So you're just given a circle and you're told to put a square in it. And let's think a bit, how do we make a square? So what makes a square a square? So we want equal sides, we want 90 degrees, okay? So a good way to do it is if we can come up with the diagonals meeting at right angles, then that's going to give us a square. Okay, so that's what we've got to start off with. So remember, we start off with nothing. We just start off with a circle. So the first thing we've got to do is find the center of the circle S with our rusty compass and straight edge. And that's going to be a homework problem for you for next week. Okay, but it's not. You can construct it. You just come up with any old radius at all. And so the next thing we want to do is come up with a diameter which is going to be perpendicular to the diameter that we've constructed for ourselves. So now we just use our rusty compass and mark off E and Z from A, and we mark off T and H from G.
Do those have any specific like radiuses when you mark off?
It's a rusty compass.
Oh,
so
sure.
A to Z is our special compass that we're given. So that's really the only length we can transmit. Okay. Okay, and so then we draw in the lines TE and TH. Okay, and they're going to be parallel and they're going to be bisected by this diameter here. Okay, and so we can use these two lines because now if we join this line to this line, so this diagonal crosses this diagonal here, it's going to meet in the midpoint of this rectangle here. And so then if we draw in SM, make it a diameter, it's going to be parallel to these guys. It's going to go through the center. So it's also going to be a diameter, and it's going to be perpendicular to our first given diameter. And so now we have our square here. And this is there's actually lots and lots of ways you can make a square. There's lots of different constructions. This is considered a nice one because it's accurate. And by accurate, I mean that if a craftsman actually uses this to make a square, the errors aren't too egregious. It'll make a good square.
Dr. Ryan,
Mm-hmm.
do they have a straight edge at their disposal?
Yes.
Okay.
So it's just a straight edge. So they've got a straight edge, but it's not a ruler. So they can.
So like if you're given the center, like you find the center, and then you just pick a random point on the outside of the circle.
You can join a line.
Okay,
exactly.
And then you can connect it all the way through.
Yeah, exactly. The first thing you do is you find S, and then you do any line through S, and that's going to be a diameter. That's what we get started with. Okay, I think I've talked for like almost 45 minutes. I think there's one more thing I wanted to talk about, but I think I'll save that for next week. Any questions about any stuff we've done? Blake, do you have a question? Okay. So